Hi guys, myself Pranab is here to deliver today's presentation, Power Transformer Part 43. As the subject is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with analyzing the tap-changer degradation mechanisms. Number one, for switching contacts, that is degradation of the tap-changer switching contacts. OLTC has basically configured with different sets of switching contacts and being entertained switching of different currents at different recovery voltages. The main contacts of the arcing switch are designed to transfer the load current to the transition contacts and thus to break the load current and the circuiting current. Whereas contacts of the tap selector and the changeover selector are not meant for switching current. Since these sets of contacts being not to switch significant currents, so practically these contacts would not wear as fast as the arcing switch contacts. However, pitting of contacts would have been exhibited with having some layer formation of so-called pyrolytic carbon, that is thermally induced chemical decomposition of organic materials in absence of oxygen. Over time, once the layer has formed on the contacts to make a stable film of low conductivity, then this formation of surface flame is thus referred to as the early stage of the long-term aging effect. Such degradation mechanism of the contacts related to the tap selectors and changeover selector would have been initiated not due to the arcs but by a long-term overheating process under oil. Again, I repeat, such degradation mechanism of the contacts related to the tap selector and the changeover selector would have been initiated not due to the arcs but by a long-term overheating process under oil. The occurrence of this surface film would have been accelerated further with the rise of surface temperature of the contacts. Infrequent movement of the contacts would have been the main reason for the formation of the surface film, as it never be wiped off while the changeover selector is at stationary condition. To eradicate this surface film at its initial stage, it is recommended for periodical movement of OLTC switching contacts through its cycle of operation. Number two, misalignment of the tap changer assembly. The position of the moving and stationary contacts, as they are not to be perfectly aligned, so the contacts would become so unreliable that may have the possibility to reduce the insulation distance between the two taps. Such happenings would have resulted a short circuit or discharge to the ground between the two taps. The short circuit current that quickly burns out the tap coil and even causes damage to the entire winding. Number 3, motor drive unit. On-load tap changer generally consists of a motor drive unit whose main objective is to drive the connected on-load tap changer to a higher or lower tap of a transformer, that is, just to adjust the transmission ratio of transformers without interrupting the load flow. A motor drive unit that receives a control impulse, which might be from a voltage regulator or changing the operating position of the on-load tap changer. Because of the designing complexity of the electric motor drive unit for tap changers, which is rather made to design as per exclusive requirement for the specific MVA rating transformer itself, so the cost for their production and assembly is become considerably high. Now, on-load tap changers that are to be selected in accordance with the key parameters of the transformer were to be fitted. 1, obviously MVA rating of the transformer, connection of tap winding for star, delta or single phase connection. Number 3, rated voltage and regulating range. Number 4, number of tap positions. 5, insulation level. 6, lightning impulse and power frequency voltage of internal insulation level to ground. Operating data of OLTC can be derived from 1, rated through current. Number 2, rated step voltage. Number 3, rated step capacity. Appropriate tap changer can be determined through OLTC resistor or reactance type, whether OLTC is of resistor type or reactance type. Number 2, number of poles. Number 3, nominal voltage level of OLTC. Tap selector size. Basic insulation level, that is BIL, basic insulation level, and basic connection diagram. The electric motor operated driving mechanism comprises of 1, an electric motor. Number 2, gearbox. Number 3, a mechanical end stop. Number 4, a position transmitter. Number 5, input or output ports, and that is IO ports, and user interface. Number 7, a control unit for controlling the electric motor drive unit. Electric motor, preferably a 3-phase motor with multi-adaptable power supply from a frequency converter in the control unit, wherefrom the motor can be supplied by 110 to 440 volt AC or DC. Again, I repeat, electric motor is preferably a 3-phase motor with multi-adaptable power supply from a frequency converter in the control unit, wherefrom the motor can be supplied by 110 to 440 volt AC or DC voltage. Number 7, that is a control unit of controlling the electric motor drive unit, which is meant for maintaining the overall control of all operation, configuration and signaling of the electric motor drive unit. Taken feedback from the position transmitter, the control unit is perfectly supervised the motor drive unit mechanism. Parameters such as speed rotation, direction of rotation, and ramp speed all are to be recorded by the control unit. The motor current signature analysis that can indicate various OLTC mechanism problems, and it is effective for maintenance point of view. If the motor has drawn current which is exceeding the design current or shown some fluctuations in the current parameter, then it is obvious that the subject motor is running against some types of mechanical forces. The current deviations that might have been cropped up due to lack of lubrication, damaged bearing, misalignment of gear mechanism, etc. Any sort of unexpected duration of a motor operation during tap positions change is an indicator of these kinds of problems. As the technology is vastly shifting towards smart grid protection and control standards, so it has been a custom for implementing remote control and monitoring of tap changer mechanism of transformer by utilizing intelligent electronic devices, IED. Supervisory control and data acquisition system, that is SCADA, is one of the basic tasks of an automatic system, that is automation system, which comprises of the following tasks as proposed on the standard IEC 61850. A. Local and remote operation of the high voltage equipment. B. Acquisition of data as imparted through the sensors. C. Handling of events and alarms. Smart grid control system that has to insist the implementation of this feature into an intelligent electronic device, which is called IED, which can monitor, control, and further communicate as on IEC 61850 standards. Therefore, monitoring of OLTC equipment is also a mandatory requirement to meet the smart grid standards. System voltage regulation through OLTCs would have been a continuous operational process by varying the tap positions in accordance with receiving raise or lower pulse from the control circuit, বা control unit rather. So, the control circuit can able to issue commands for change of tap position only when the current position of the tap changer has to be identified by the control circuit. Suitable transducer are thus to be provided to monitor the existing tap position as well as to convert the position of the tap changer to have a current output. The output signal is thus to be connected to one or several receiving instruments such as panel indicators, recorders, controller, IEDs, etc. VLTC controller, which is designed with such IEC, will provide all the benefits applicable for smart grid system to run and also extend additional benefits for fault analysis and system study. This concept contributes an object-oriented approach with logical nodes, and that can help to establish a clear understanding for taking stepwise functional activities related to protection status of the equipment. Effective control mechanism for reliable and faster operation of changing power transformer tap positions. At the present context, the on-load tap changers are mostly used for high voltage regulating system, and the switching operation for varying tap positions is precisely controlled by using an automatic voltage control relay, AVCR, automatic voltage control relay. Due to restructuring of power utilities and also for modulation to improve system stability, the modern management of transmission system network has become highly complicated. The transmission network is of the combination of the transmission line and the brand of power transformers, which are of the high inductance electrical equipment. Particularly in high voltage system, power transformers of three-phase star-connected transformers having one terminal grounded would have been frequently designed and built with the insulation level as graded to other windings and grounds, and this has to be maintained in order to entertain the normal frequency voltage stress. Again, I repeat, particularly in high voltage system, power transformer of three-phase Y connection having one terminal grounded would have been frequently designed and built with the insulation level as graded to other windings and ground, and this has to be maintained in order to entertain the normal frequency voltage stress. In that case, if the power transformer is subject to have transient voltage excitation, then there will be a local concentration of voltage in the winding, and that may raise the voltage to ground at intermediate points above the terminal voltage. Such occurrence may lead to flow capacitance charging current of the coils to ground through the transformer winding, causing a different form of stresses on its insulation part, that is transformer insulation part. The failure of insulation may have been taken place once the distribution and magnitude of the imposed voltage stresses would have been exceeded from the stipulated design value of the withstanding voltage stresses. There are several factors that may affect the power quality both at distribution voltages and transmission voltages. Power quality problem as due to oscillatory transients, voltage dips or voltage sags, short interruptions, steady state deviation through harmonics and flicker, etc., may first have to occur disturbances at higher voltages, and then that will be transmitted to lower voltage systems via transformers. Let's stop here, further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share and subscribe. Your subscription would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.